Okay, in this video I'm going to start in the packet that you got from the bookstore going through for Chapter 9, Torque and Rotational Equilibrium. The learning objectives listed are calculate torque for a given force about a chosen or given axis of rotation, draw a rigid body free body diagram. This is a little bit different than the way we've been drawing free body diagrams in the past because where the forces are located is really important in this chapter. We're going to learn how to strategically select an axis of rotation so that we can make the calculations easier and still be able to find the unknown values. And then we're going to solve for unknown values using the three equilibrium conditions, which is sum of forces in the x direction equals 0, sum of forces in the y direction equals 0, and the summation of torque equals 0. All right, and I guess while talking about learning objectives, we are not going to do anything where the rotation is not in equilibrium, which is found in Chapter 10 in this set of slides and videos here. All right, so imagine you live in an old house and you're trying to close a door that's stuck because the bottom of the door scrapes against the floor. So I've been in lots of houses like this. There's an awesome beach house that we go to, and this happens all the time. So the door is 0.75 meters wide, and we're supposed to draw a picture of the top view of the door. So if you were up above a door, standing on a ladder and looking down, the door would just look like this, and you'd be able to see the doorknob in the top, and you'd be able to see the hinges. Okay, so the hinges would be here. So basically it's pivoting about this. So there's your pivot point. So what is the maximum distance from the pivot point that the force can be applied? Well, it's 0.75 meters. We could apply a force right here. So I guess if we were applying a force to close it, it would be right there. So there's our force. Okay, say force of our hand, F sub h. And so the furthest away we could get that would be 0.75 meters. That's the full width of the door. Okay, 0.75 meters. What angle between your force and the plane of the door will give you the best chance to move the door? Well, as it was drawn right there, 90 degrees. That's the best angle. If you apply a force of 100 newtons, what is the maximum amount of torque you can create relative to the pivot point? Well, torque is equal to Fr sine theta. So the maximum amount of torque would be to apply that 100 newtons, put it as far away from the pivot point as possible, which we said was 0.75 meters, and then we apply it at a 90-degree angle, because the sine of 90 degrees is equal to 1. You go ahead, plug it into your calculator, and you'll see. And so 100 times 75, that would be 75 Newton meters. And I just want to note that here, a Newton meter is not a joule. I know when we're talking about work, a Newton meter is a joule. If you apply a Newton of force to something and that object moves 1 meter, that is 1 joule of work. But here, we're talking about equilibrium, we're talking about torque, and the object's not even moving. The force is applied perpendicular to this lever arm R, which is the position vector of the force relative to the pivot point, rather. And so, to make a long story short, when we're talking about torque, use units of Newton meters. When you're talking about work or energy, then you're talking about joules. All right, if the door does not move, how much torque is created in the opposite direction by the force of the floor rubbing on the bottom of the door? Well, it must be 75 Newton meters, but in the opposite direction. Okay, so if we look here, we're going to say that counterclockwise is our positive direction for torque. Okay, and this is the Greek letter tau for torque, not T, not capital T. And so this downward force is creating a positive torque because that's going to cause the door to rotate in a counterclockwise direction, and that's what we call positive. And so the torque created by our force was positive, and this one is going to be negative. So, opposite direction. I've already taken care of that with the sign now. What if you applied the force at a 45-degree angle instead? And so if we do that, say okay. So we got our pivot point here, and the force was either like this or like this. It doesn't matter. It's going to create the same amount of torque either way. That's a 45-degree angle. So there's our 100 newtons, or over here, 100 newtons. And then we still have the 0.75 meters. These distances, it's really important to put the distances on these free body diagrams that we're going to be drawing in this chapter, and we're going to go into more depth on that. But the torque, and again, Greek letter tau, not T, which is tension. Okay, we want to keep those straight. So tau would be 100 newtons times 0.75 meters times the sine of 45 degrees. Grab my calculator. Make sure I'm in degrees. And that comes out to 53.0 Newton meters. And so you can see by pushing at a different angle than 90, you're going to get less torque. And as I said, it doesn't matter which way the force was angled, it's going to be less torque either way. Alright, now we're looking at a diagram, and there's a rod there. And so if we want to look at the torque, torque is always relative to something. We have to think about what it's relative to. So if we're doing it relative to the center of the rod, we would say, okay, well this force over here is 0.6 meters away, and this force is 0.6 meters away. So the distance is the same. The arrows may not look like it, but the forces are the same magnitude. The only difference is the angle, and so the force that's going to create the largest amount of torque is F1. Okay, so the magnitude of the position vector, size of the force are the same. The only difference is the angle. Here's another question though. Which force produces the largest torque relative to the left end of the rod? And so let's consider that. For this question. So if we're looking relative to this axis of rotation, F1 is not going to create any torque whatsoever. That's like trying to open the door by pushing on the hinge. You're not going to get any rotation at all. So if this is our axis of rotation, we get no torque whatsoever created by F1. So F2 is definitely going to produce more torque. As we're going to see later, we get to actually pick what the axis of rotation is, because the objects that we're studying are not going to be rotating, because in chapter 9 it's rotational equilibrium. So if none of the objects are rotating, we can actually pick any axis of rotation we want, whatever's convenient for us to be able to do the calculations. And that's going to help speed along our calculations, makes them easier, and less chance for mistakes. Alright, now we have a couple more examples here. Find the torque produced by the force shown relative to this axis of rotation. So axis of rotation is going to get abbreviated a lot by AOR. So that's our axis of rotation, and so the torque is simply 150 newtons times 2.3 meters times the sine of, oh, you might be tempted to just jump in there and do 40 degrees. But watch. My position vector R here and my force vector F, the angle is this angle. So the angle is actually 50 degrees. Okay? So if you had just put 40 in there, you would have been off by a notable amount. Not a lot, but it definitely is the wrong angle. So you want to make sure you're using the right angle. And this comes out to 222. Hold on. I think I might have typed in the wrong angle. I did, in fact. Ha! So 264. So 50 degrees is the right angle, and tau, the correct angle. Gotta be careful not to say right angle, because that has its own meaning. So 264 Newton meters. Find the net torque produced by the forces shown about an axis of rotation in the center of the beam and perpendicular to the page. Alright, so 0.6 meters is the distance from the axis of rotation to the 200 Newton meter force, and then 0.6 meters is also the distance over to that other 200 Newton force that's at an angle. And we're going to call counterclockwise our positive direction for torque. So the net torque is equal to torque 1 plus torque 2, which is equal to 200 newtons times 0.6 meters times the sine of 90 degrees. So that's based on this one. Minus 200 newtons times 0.6 meters times the sine of 65 degrees. Sorry, this is going a little downhill here. I didn't plan very well. But this force right here, compared to this axis of rotation, is going to cause a clockwise rotation. Okay, a clockwise rotation. And so that's the negative direction, so that's why I put a negative sign there. So this force here, creating that torque. And so now we can figure out our net torque. And it is going to be positive because this is just like the question on a prior slide where we did it qualitatively. Here we're doing it quantitatively. So 200 times 0.6, I don't even need to multiply times sine of 90 because I know that's 1, minus 200 times 0.6 times the sine of 65, and I get 11.2 Newton meters. Okay, that's a good place to stop.